A sieve analysis is a practice or procedure used to assess the particle size distribution of a granular material. The size distribution is often of critical importance to the way the material performs in use. A sieve analysis can be performed on any type of non-organic or organic granular materials, including sands, crushed rock, glazed granite, feldspars, coal, soil, a wide range of manufactured powders, grain and seeds, down to a minimum size depending on the exact method. Being such a simple technique of particle sizing, it is probably the most common procedure. A gradation test is performed on a sample of aggregate in a laboratory. A typical sieve analysis involves a nested column of sieves with wire mesh cloth. See the separate mesh page for details of sieve sizing. A representative weighed sample is poured into the top sieve, which has the largest screen openings. Each lower sieve in the column has smaller openings than the one above. At the base is a round pan, called the receiver. The column is typically placed in a mechanical shaker. The shaker shakes the column, usually for some fixed amount of time. After the shaking is complete, the material on each sieve is weighed. The weight of the sample of each sieve is then divided by the total weight to give a percentage retained on each sieve. The size of the average particle on each sieve is then analyzed to get a cut-off point, a specific size range, which is then captured on a screen. The results of this test are used to describe the properties of the aggregate and to see if it is appropriate for various civil engineering purposes, such as selecting the appropriate aggregate for concrete mixes and asphalt mixes, as well as sizing of water production well screens. The results of this test are provided in graphical form to identify the type of gradation of the aggregate, a suitable sieve size for the aggregate underneath the nest of sieves to collect the aggregate that passes through the smallest. The entire nest is then agitated, and the material whose diameter is smaller than the mesh opening pass through the sieves. After the aggregate reaches the pan, the amount of material retained in each sieve is then weighed. Preparation. In order to perform the test, a sufficient sample of the aggregate must be obtained from the source. To prepare the sample, the aggregate should be mixed thoroughly and be reduced to a suitable size for testing. The total weight of the sample is also required. Methods. There are different methods for carrying out sieve analyses, depending on the material to be measured. Throw-action sieving. Here a throwing motion acts on the sample. The vertical throwing motion is overlaid with a slight circular motion, which results in distribution of the sample amount over the whole sieving surface. The particles are accelerated in the vertical direction. In the air they carry out free rotations and interact with the openings in the mesh of the sieve when they fall back. If the particles are smaller than the openings, they pass through the sieve. If they are larger, they are thrown upwards again. The rotating motion while suspended increases the probability that the particles present a different orientation to the mesh when they fall back again, and thus might eventually pass through the mesh. Modern sieve shakers work with an electromagnetic drive which moves a spring mass system and transfers the resulting oscillation to the sieve stack. Amplitude and sieving time are set digitally and are continuously observed by an integrated control unit. Therefore, sieving results are reproducible and precise. Adjustment of parameters like amplitude and sieving time serves to optimize the sieving for different types of material. This method is the most common in the laboratory sector. Horizontal sieving. In a horizontal sieve shaker, the sieve stack moves in horizontal circles in a plane. Horizontal sieve shakers are preferably used for needle-shaped, flat, long or fibrous samples, as the horizontal orientation means that only a few disoriented particles enter the mesh and the sieve is not blocked so quickly. The large sieving area enables the sieving of larger amounts of sample. For example, example as encountered in the particle size analysis of construction materials and aggregates. Tapping. Sieving. A horizontal circular motion overlies a vertical motion which is created by tapping impulse. These motional processes are characteristic of hand sieving and produce a higher degree of sieving for denser particles than throw-action sieve shakers. Supersonic sieving. The particles are lifted and forcibly dropped in a column of oscillating air at a frequency of thousands of cycles per minute. Sonic sievers are able to handle much finer dry powders than woven mesh screens. Wet sieving. Most sieve analyses are carried out dry, but there are some applications which can only be carried out by wet sieving. This is the case when the sample which has to be analyzed is e.g. a suspension which must not be dried, or when the sample is a very fine powder which tends to agglomerate in a dry sieving process. This tendency would lead to a clogging of the sieve meshes, and this would make a further sieving process impossible. A wet sieving process is set up like a dry process. The sieve stack is clamped onto the sieve shaker and the sample is placed on the top sieve. Above the top sieve a water spray nozzle is placed which supports the sieving process. Additionally to the sieving motion, the rinsing is carried out until the liquid which is discharged through the receiver is clear. Sample residues on the sieves have to be dried and weighed. When it comes to wet sieving, it is very important not to change to sample in its volume. Air circular jet sieving. Air jet sieving machines are ideally suited for very fine powders which tend to agglomerate and cannot be separated by vibrational sieving. The reason for the effectiveness of this sieving method is based on two components: a rotating slotted nozzle inside the sieving chamber and a powerful industrial vacuum cleaner which is connected to the chamber. The vacuum cleaner generates a vacuum inside the sieving chamber and sucks in fresh air through the slotted nozzle. When passing the narrow slit of the nozzle, the air stream is accelerated and blown against the sieve mesh, dispersing the particles. Above the mesh, the air jet is distributed over the complete sieve surface and is sucked in with low speed through the sieve mesh. Thus the finer particles are transported through the mesh openings into the vacuum cleaner. Types of gradation. A dense gradation. A dense gradation refers to a sample that is approximately of equal amounts of various sizes of aggregate. By having a dense gradation, most of the air voids between the material are filled with particles. A dense gradation will result in an evened curve on the gradation graph. Narrow gradation, also known as uniform gradation. A narrow gradation is a sample that has aggregate of approximately the same size. The curve on the gradation graph is very steep, and occupies a small range of the aggregate. Gap gradation. A gap gradation refers to a sample with very little aggregate in the medium size range. This results in only coarse and fine aggregate. The curve is horizontal in the medium size range on the gradation graph. Open gradation. An open gradation refers an aggregate sample with very little fine aggregate particles. This results in many air voids because there are no fine particles to fill them. On the gradation graph, it appears as a curve that is horizontal in the small size range. Rich gradation. A rich gradation refers to a sample of aggregate with a high proportion of particles of small sizes. Types of sieves. Woven wire mesh sieves. Woven wire mesh sieves are according to technical requirements of ISO 3310-1. These sieves usually have nominal aperture, ranging from 20 micrometers to 3.55 millimeters, with diameters ranging from 100 to 450 millimeters. Perforated plate sieves. Perforated plate sieves conform to ISO 3310-2 and can have round or square nominal apertures ranging from 1 millimeter to 125 millimeters. The diameters of the sieves range from 200 to 450 mm. American Standard Sieves. American Standard Sieves, also known as ASTM sieves, conform to ASTM E11 standard. The nominal aperture of these sieves range from 20 micrometers to 200 mm. However, these sieves have only 8 and 12-inch diameter sizes. Limitations of sieve analysis. Sieve analysis has, in general, been used for decades to monitor material quality based on particle size. For coarse material sizes that range down to number 100 mesh, a sieve analysis and particle size distribution is accurate and consistent. However, for material that is finer than 100 mesh, dry sieving can be significantly less accurate. This is because the mechanical energy required to make particles pass through an opening and the surface attraction effects between the particles themselves and between particles and the screen increase as the particle size decreases. Wet sieve analysis can be utilized where the material analyzed is not affected by the liquid, except to disperse it. Suspending the particles in a suitable liquid transports fine material through the sieve much more efficiently than shaking the dry material. Sieve analysis assumes that all particle will be round or nearly so and will pass through the square openings when the particle diameter is less than the size of the square opening in the screen. For elongated and flat particles, a sieve analysis will not yield reliable mass-based results, as the particle size reported will assume that the particles are spherical, where in fact an elongated particle might pass through the screen end-on, but would be prevented from doing so if it presented itself side-on. Properties. Gradation affects many properties of an aggregate. It affects bulk density, physical stability, and permeability. With careful selection of the gradation, it is possible to achieve high bulk density, high physical stability, and low permeability. This is important because in pavement design, a workable, stable mix with resistance to water is important. With an open gradation, the bulk density is relatively low due to the lack of fine particles. The physical stability is moderate, and the permeability is quite high. With a rich gradation, the bulk density will also be low, the physical stability is low, and the permeability is also low. The gradation can be affected to achieve the desired properties for the particular engineering application. Engineering applications. Gradation is usually specified for each engineering application it is used for. For example, foundations might only call for coarse aggregates, and therefore an open gradation is needed. Sieving with digital image processing. Digital image processing to determine PSD has now become the quickest and easiest method for analyzing rock masses. The algorithms used to analyze digital images and produce PSD has been researched and developed at the University of Arizona since 1997, and now in software offered by multiple companies around the world. The method for digital image processing is the following: image acquisition. Using a standard digital camera, a user takes a picture of the rocks for analysis. Loading image into the program, typically user-friendly, either through a file or drag-and-drop processing image with software's proprietary algorithm. The software analyzes individual pixels' gradient and compares to each of the neighboring pixels to determine boundaries between the rocks. Editing. User edits the boundaries to better accuracy. Results. PSD is produced by the program. The results page is typically customizable for reporting units and graph style. Real-time data reporting of image processing. Also available is real-time data reporting from any desired location within the comminution circuit. Continuous conveyor belt fragmentation measurements in the comminution plant can provide an instantaneous tool for process control. When planning the integration of fragmentation measurement instrumentation, position your camera monitoring station in a location where you can effect a process control change based upon the particle size information you receive. For example, the primary crusher product is a good location to measure, since you are able to control the size that the crusher is producing with slight adjustments to the crusher, ensuring that the downstream comminution circuit is receiving a consistent product to help reduce variability in the process. In addition to the continuous particle size analysis, the database of belt material size can be used for simulations and for further process analysis to help increase process efficiency and throughput.